The next question. A baseball player hits a baseball at a height of 0.9 of a meter above the ground at an angle of 40 degrees, given the ball a speed of 44 meters per second. Okay, so we'll just put the ground here, and the ball starts here, and that is a height of 0.9 meters above the ground, and the baseball is hit off here at an angle of 40 degrees and at a speed of 44 meters per second. So obviously this has a horizontal and a vertical component. This is 44 cos 40, and this is 44 sine 40, and the baseball travels up and comes back down here on the ground, obviously, and we are looking first for how far does it travel horizontally. So before we can get that, we need to get the time taken. So we're looking only at the vertical components, u, v, a, t and s. U is 44 sine 40, v we don't know, a is minus g, t is what we want, and s is minus, and the minus is important, 0.9, because the ball is 0.9 of a meter vertically lower than when it started. So using the formula, S equals U T plus a half A T squared. So this can be simplified to 4.905 T squared minus 44 sine 40 minus 0.9 equals 0. This is a quadratic where that is A, that is B, and that is C. So just using the quadratic formula, we'll get um, 4.905 minus 44 sine 40, and then minus 0.9. Should get two answers, a negative and a positive. So 5.8, or I'm sure the second answer here will be negative. Yeah, negative. So taking the 5.8, we can get the range now. So it travels for 5.8 seconds horizontally. So looking in the horizontal direction now, the range is how far it travels horizontally, and horizontally is just distance, speed, time, since there's no acceleration. So it will be the speed, which is 44 cos 40, multiplied by the time, which we said is 5.8. So hitting that now in on the calculator. 44 cos 40 times 5.8, and that's 195.5 meters. Okay, so that's the first half. So now for the second half, nearly the same, except I'll tell you that there's a friction force. So as the ball is traveling through the air, there's a friction force which I say acts downwards and backwards. So in other words, there's a force here of 0.1 newtons, and there's a force here of downwards 0.1 newtons. Now actually I just realized there's a small typo in the question, so it doesn't quite make sense. Well, it does make sense, but it's actually a little bit too hard, because really what's happening is the friction should be acting this way on the way down, but then acting the other way on the way up. So actually no, even though it is a bit harder than I was picturing it was going to be, I'll still keep it that way, but it will be a little bit harder. We'll have to break the flight up into two halves. So firstly, the baseball starts here, goes up, reaches a maximum height, and then comes back down. On the way up, there's a force acting down, which is its weight, which is mg. Also there's a friction force acting backwards here of 0.1, and in addition to this there's a downward drag force of 0.1 newtons as well. Okay, so let's get the time taken to reach the maximum height. So we have U, V, A, T, S. So just like before, we can resolve here. Horizontally, this will be 44 cos 40, and this one here will be 44 sine 40. So U is 44 sine 40, V is 0, A, not 100% sure what it is because it could be a little bit different because we have the drag force. T we don't know, and S we don't know, so we better get the A. So from Newton we know that F equals ma, so A will be F over m. So in this case that would be 0.1 plus, and the weight here, m multiplied by g, is 0.1019 multiplied by 9.81, which works out to be 1. So the total force is 1.1 over 0.1019 then. So this is from the drag, and this one here, and this one here is from the weight. Sorry, I'll make that 1.0. So it's 1 plus 0.1, which is 1.1 over 0.1019. And this should not be the same as 9.81. So 1.1 divided by 0.1019. So it's larger now, it's 10.79. So it will be accelerating faster to the ground because of the drag force. Okay, now we can get the time to the maximum. So that's V equals U plus A T. So T will be 44 sine 40 over 10.79. So this is just half the time, roughly. 44 sine 40 divided by 10.79. So that's 2.62 seconds then for the first part. Now, for the second half, going down, the only difference here is that this drag force is acting upwards. So it just means that here it'd be 1.0 minus 0.1. So on the way down, the total force downward is 0.9. So that would become instead 0.9 divided by 0.1019, which is 8.83 meters per second squared. Okay, now that we have that, we can get the time to go from the maximum down to here. Let's write down the information. So U is, again looking vertically, is 0. V we don't know. A is minus 8.83. T is what we want, and S we don't know, although we could work S out. It will be 0.9 plus whatever the height was from the previous part. So let's work that out here, the previous S. We can go with UT plus a half A T squared. So let's get that height now. 44 sine 40 times 2.62 minus 10.79 over 2 times 2.62 squared. So that height is 37 plus the 0.9. So the total is 37.96. So that would be 37.97 then in total. Okay, so we're still looking for the time. We'll have to go with S equals U, which is 0, T plus a half A T squared. So it will be 37 0.97 times 2 over 8.83, and then square root. Okay, so that time is 2.93 seconds. So adding that to the time we got earlier, that is 5.55 seconds. So after all that, we're finally able to get the range. The range is the distance it travels horizontally. But this time we have to use UVATS horizontally because there is an acceleration caused by the drag force. The U is still what we had a moment ago, 44 cos 40. The V we don't know. The A we have to work it out. It's F over M. The T we do know is 5.55, and the S is what we're looking for. So that would be 0.1019 as the mass, and then above that is the force, which is minus 0.1. Okay, so let's just work that out. Minus 0.1 divided by 0.1019, so that comes in at a deceleration of minus 0.981. Okay, so now we can get the S. We'll go with S equals U T plus a half A T squared. Okay, so 44 cos 40 times 5.55 minus 0.981 over 2 times 5.55 squared. So that comes in at 171.96, so 172 meters for the S. So in the previous question, part A, it was 195.5, and now it's 171 meters, 172 meters. So a substantial difference between the two because we considered friction. This question actually was a bit harder than what I was picturing when I wrote the question. But anyways, it's a good example of how much more difficult it is to deal with projectiles that have friction both horizontally and vertically.